Okay. So yeah, I think that's the time. Yeah, I think you will be surprised to see me standing here, not Professor Han, because he is out of town this week to attend some important conference, and he will be back on this Thursday. So don't worry, but I will be back next week because he will be out of town again. And so let me introduce myself. I'm Xiangren. I'm a fifth-year PhD student in data mining research group at UIUC. So, oh yeah, sure. Sorry, I think I'm not quite familiar with this. Did Professor Han usually hold these things in hand, or he was just put it somewhere? Okay. I don't have a good job. How does? So I think I need to speak louder. How does this sound? The last row. Can you hear me? Oh, cool. So I'm Xiangren. I'm a fifth-year PhD student in the data mining research group here, and I'm quite honored to be giving this lecture. Basically, continue the contents of the class analysis. So I'm pretty excited because I can still clearly remember the days actually sitting like one of you here, and I'm seeing those slides with too many words, but I can't help too much. I can't change the size, so I hope this will be better later. And I understand that all of you just come back from the break, so hopefully the content today I'm going to introduce won't be too intensive. To be continuing, last time I think you all talked about this partitioning-based clustering algorithm. The partitioning method is basically saying that you have a specific number of the clusters in mind, let's say K, and you want to try to partition the data points or the data objects at hand into these K different clusters, where the clusters should be within those clusters, they should be data points should be similar to each other as much as possible, and inter those clusters, they should be dissimilar to each other as much as possible. So remember that the partitional-based method compared to other methods is that it has a specific number of clusters in mind. This will be the advantage, and also will be the disadvantage, because in some applications, you are quite clear that okay, for the consumers, you want to segment them into, let's say, K different segments. Based on some preliminary study, you know this K is making sense. But when you are doing some more like exploratory data mining tasks, you actually have totally no idea about the data distribution. So you have no idea about this K in mind. And that comes to the motivation to design other kinds of clustering algorithms other than these partitional-based methods. So I believe last time Dr. Han introduced the most popular and widely adopted algorithm, and also very simple algorithm called K-means algorithm. Basically, you have this K in mind, and what you are doing here is you try to first randomly assign K different data points as the so-called central of the clusters. So this process, this pre-processing is randomly done. And then starting from this K central, you try to assign the remaining data points to these K different clusters by using some predefined distance measures. So I think Dr. Han introduced those different kinds of distance measures and distance functions. So then you can try to measure the similarity between any two data points in this picture. And after these steps, you basically have an initial assignment of the data points to these K different clusters. Here, in this example here, you can see the K is equals to 2, and you have these red color points and blue color points representing two different clusters. And the second picture basically shows you that after the assignment, some data points got the red color, some data points got the blue color, and the next step is to adjust the central for the cluster. This basically categorizes the K-means algorithm. In K-means, the central is computed as basically the average or the mean of these data points. So it's a numeric mean value instead of other definitions. So after you recomputing these means for the K clusters, you basically have the new centrals for each of the K clusters, and then you can iteratively redo this process until the whole process converge. By converge, there will be different criteria. Some people will say, okay, there will be less than n data points will be moved in the next step. That can be treated as a converge. Or you can think as the objective function value doesn't change much relatively. That can also be seen as another criterion for converge. So this is the basic idea of the K-means algorithm. And here comes the slide. I believe last time Dr. Han stopped at the end of the class. So, there's some obvious disadvantage of the K-means algorithm. One of them is definitely the very sensitivity to the noise or the outliers. So think about when you have a a trading firm company and you want to partition the employees in terms of their salaries. So of course, in the trading firm, you have some executive level employees. They will earn like millions of dollars each year, versus there are some like bottom employee. They can be earning like just hundreds of thousands of dollars each month. So if you're using K-means algorithm in this specific case, you will see those executive level employees actually are looking kind of like outlier in this scenario. They will kind of drag the whole distribution to a very biased point. First, and remember, the population of those outliers is actually very, very small. There could be only like tens of different executive level employees versus the remaining maybe hundreds of thousands of employees. So taking the mean value to represent to recompute the central for each cluster, it's a very risky move in this case. That actually motivates the needs from switching to using mean value to other kind of definition to define the central of a cluster. And in this slide, it actually talks about how we can use the midpoint. And I will define what is the midpoint here to replace the mean value. So the midpoint here actually means the central data point in the cluster. So remember, midpoint here basically represents a specific data point or data objects in your data set. And you taking the central data points as the midpoints, actually you can avoid this outliers effect. You think about even in a cluster you have like 5 executive level employee and the remaining one maybe hundreds of different employees. Taking the midpoint actually can kind of ignore those effects caused by the executive level employees. And here is, and the way that the K-midpoint clustering algorithm works is very similar to the K-means algorithm, except for that how you compute the central for the cluster. Let's take a close look at this algorithm's outline. So you first select K points as the initial representative objects, and also you can think as just selecting the initial K midpoints. And then you try to assign each of the remaining data points to the cluster with the closest midpoint. This step is basically same as the K-means algorithm. And the next step will be different from K-means, is that you randomly select a non-representative data point or object, OI, and then you compute the cost if you swap this data point with the original midpoint and use this data point as the new midpoint. What would be the cost? So the cost here will be computed in terms of how you define this objective function or the arrow function. So if this operation will lead to a cost, will lead to a negative cost, meaning that you are actually improving the arrows of the whole picture. So you are reducing the arrow of the whole picture. Then the algorithm basically say yes to this movement, so you can do this swapping. And if the swap cost is actually larger than 0, meaning that it actually increase the error, then the algorithm say no to this movement. So that's how the k-medoid work. And this process will be iteratively done until some convergence criterion is satisfied. So here would be a more intuitive example of the how the k-medoid work. The PAM here is basically a specific k-medoid algorithm, or with a certain paper they mentioned about it. So you can see from the first picture, you basically want to cluster this group of data points, and you have k equals to 2 in mind. And first, you randomly select 2 data points from this big picture, and which is the highlight as the deep blue color nodes in the second picture. And then you try to assign the remaining data points to these 2 clusters. Basically, you try to compute the distance of those data points to the two medoids. And then in the fourth pictures in the bottom, you can see the algorithm proposed a new data point as the medoid, which is shown in the light blue color there. And the algorithm asks whether doing such swap will actually decrease the error. And the algorithm actually found out no, this node is actually not helpful. So it picked another node eventually, which is shown in the orange color node. And that node turned out to be a better node than the original deep blue color node. And that forms the new medoid for the cluster. And this process will be iteratively done. So basically, the k-medoid algorithm, as I just mentioned, is the core idea is to find the representative data points or the data objects in the data sets instead of computing a numerical mean value for those data points. So all the operation is done on data objects you have in hand. And that PAM algorithm I just described is actually a 1987 paper. It's pretty old, but still quite well-cited paper. The main problem, the algorithm I just described, give you an overview picture of how it works, but there are some actually technical details I haven't mentioned. One of them is how you define this cost or the errors when you're doing those swapping. So there will be different ways of defining this cost. One of them definitely can be, as you previously saw, the sum of the square errors defined by the L2 norm there. And you check whether this swap will actually reduce the SSE criterion. If yes, you do the swap. If no, you don't do that. And this PAM framework actually are pretty effective for those small data sets. But if you think about the complexity, the computational complexity of the algorithm, it's actually not very scalable, because every time when you do the swap, you need to recompute the sum of the square error criterion, and that leads to the total computational cost will be k multiplied n minus k squared, and this will be quite expensive. So following up this PAM algorithm, there's a lot of other efforts. They're basically trying to make this algorithm more efficient in terms of both the computational time complexity and also the space complexity, and trying to improve the algorithm. And you can see the best, one of the strategies they're trying to improve this algorithm is to do some sampling check. The sampling check, basically, the intuition behind that is basically saying that you don't need to exhaust all the possibility when you're doing those swapping. You're just trying to look at a local smaller region and consider those smaller regions as the candidate, and then do the swapping. So this actually reduces the original, let's say, n possibility to a t possibility, where t is the sample size you propose. So yeah, actually before this slides, I want to ask you guys a question. So we talk about this k-medoid clustering algorithm, That's mainly because it's more robust to the outlier in the data sets. Think about the executive employees' salaries case. So what other possibility you can come up with to also be robust to the outlier in the data set? You think about, basically my question is how you can define the central of the cluster that is robust to the outlier in the data set. Can you come up with other case, not the Lidoy case, like some other case? Anyone want to? Yes. Oh, that's a good point. So he mentioned that if we assume that the data points follow the Gaussian distribution, then we probably can think about the standard deviation. It will be can be think about as the noise, and then taking the data points that within a certain standard deviation. That's a very good point, and that's actually more sophisticated than what I'm going to talk about. So I'm going to talk about, from the name of this algorithm, is pretty obviously we use the median instead of the Lidoy to be the cluster centroid. And this can also be robust to the outlier because we think about the same example here. If you're taking the median salary within the whole batch instead of taking the mean, the median will be making more sense, right? And the k-median algorithm works in a very, very similar way as the k-means, except that how you define is central. So instead of computing the mean value for each cluster as the central, you just take the median of the cluster as the central. And you can use different kind of distance measures to measure the similarity between the data points. And so here, in this specific slides, you can see they use this criterion function based on the L1 norm, which is just the Hamilton distance, and to compute the mean errors for the k-median algorithms. So still, you select k points as the initial centroid for the initial representative objects, and then you repeat the steps that you first assign the remaining data points to its nearest the medium or the nearest the cluster centroid, and then we compute the medium using the new cluster membership, and then do this process until it converges. So what we just talked, yes. Oh yeah. So it's so actually that's a good question. Actually, so we're pretty clear that k-medians is actually taking the median data points as the central, right? So that you're and then in the k-Lidoy case, you actually you don't really have a very clear definition of what is Lidoy, because it just say it's most centrally located data points. But actually, it's defined in a very mathematical way. That depends on how your cost function is defined. Because the Lidoy is defined in a way that if you swap in the data points, it will not further increase the error, right? So it means that the error is very critical for determining this Lidoy data points. And the error can be defined in various ways. It could be a mean square error. It could be a L1 error, right? So actually, I would say in some case, the k-Lidoy algorithms actually could be giving the very similar results as k-median, but that's very sensitive to the concrete arrow function or objective function you're going to use. If that answers your question. Mm-hmm. So I think it's very similar, but I think it could be still there will be subtle difference because in the k-medoid algorithm, you are doing this swapping function and you look at the global objective function versus in the k-medium algorithms, you try to assign data points to its nearest median. So this step is slightly different from swapping and checking the objective function. It could lead to different results. I won't say they are exactly the same, but they are very similar. Let's even say when we only look at the objective function as divided as the L1 or the Hamilton distance, I think they will still be slightly different because the operation they are doing is slightly different. One is looking at the global objective function's value change. One is look at the local data point assignment. So you still think they kind of can be, you still think the k-medium algorithm can be a special case of the k-medoid algorithm? But I won't say the k-medoid is giving you the global optimum. None of these algorithms can give you the global optimum, but it's more looking at the global picture than the k-medium algorithm. That's what I would say. Because none of these objective functions is solved in a exhaustive way, like the k-means. I think Dr. Han discussed about before. If you exhausted all the possibilities, the complexity will be exponential of data points. That's actually invisible. So they resort to those greedy algorithms, and that will not give you the global optimum. And that's the same case here. So for k-medoids, you can also choose to exhaust all the partition of the data points. That will be the global optimum, but this way, the algorithm listed here is actually still a greedy algorithm. Does that answer your question? Okay. Yeah, feel free to ask questions. I think the content we are going to cover today is not very intensive, so I would like to have more discussion about the details. I see. So I think in this case, that's good point. So I think when they initially designed these k-medium algorithms, they actually put them in a very intuitive way. I think they only deal with the one-dimensional or two-dimensional case. When it goes to a high-dimensional case where the dimension d is larger than 2, I think the definition of the medium is also kind of defined by that objective function listed here. As you can see in that paper, they use L1 distance function, and then they compute, they're trying to find the nearest points in terms of the L1 distance. And then when they would compute these mediums, they're basically trying to optimize this objective function to make this as minimal. Right? So in terms of these steps, it's very similar to the k-medoid algorithm, I would say. But once you have a clear definition of what is the median within those data points, it will turn out to be different from the k-medoid algorithm. So I think that's a very good question. We can take this offline or to the Piazza. I believe our TAs can give better explanation if my explanation cannot come to this. I actually don't do, honestly, I don't do very deep study on how these papers really define this medium when the dimension is larger than 2. Thank you. So, any other questions? Cool. So the k-means, the k-median, the k-medoid, all these three algorithms, they actually work, as you can see, kind of divided in terms of the numerical value space. where you have in the numerical space, you have a very clear way to use either L1 or L2 norms to define the distance between the data points, and then use those distance functions to define the error function for the whole clustering process. Now, if we move from the numerical case to this categorical case, when you want to handle categorical data, for example, you have a product, and you know these products has several different functions. And let's say you have a universal space of product functions there, and one product can only cover a certain smaller subset of those functions. Then this forms a very nice categorical data clustering problem. You want to group those products in terms of their functions. So the k-means definitely cannot handle the non-numerical case very well, because when you try to map those numerical values to just 1 and 0 in the numerical vectors, the results turn out to be not doing very well, especially in the high-dimensional case. And that motivates people to develop this called k-modes algorithm. It's basically an extension to the k-means, except that they have their new definition on how to compute the distance or the similarity or the dissimilarities between two data points. So here, as you can see, if you have an object X and you have a cluster Z, or sorry, the Z is the central of the cluster L, let's say, you want to measure the distance between this object X and object Z. So the k-modes algorithms define in the following way. They basically look at the trace attribute of that object and ask whether, in terms of this trace attribute, whether these two data points have same attribute value. And if they have the same, if they don't have the same attribute values, then basically the dissimilarity measure gives the value 1, basically saying these two items are actually not similar to each other. And if the trace attribute value of X and Z are the same, then the dissimilarity is defined in the way that is 1 minus the NJR over NL. So here, NL is the number of the objects in the cluster L. The cluster L basically is where the central Z is in. And the NJR is basically asking how many number of objects in this cluster L has the attribute trace value is R. So the R here, I think Dr. Han didn't put any reference here, but R is actually the value of Xj and Zj, because Xj equals to Zj in this case. So let's assume R is Xj, and the NJR basically is computing the number of objects in the cluster L where their J attribute value equals to R. So this dissimilarity function is actually looks pretty like strange, but actually basically the idea behind it is saying that if an object has the same attribute value with many of the objects in that cluster, then they should be more similar. So that this similar score will be small, meaning that they are very similar. So using this with these similar measures, we basically can follow the same procedure as that in the k-means algorithm. We can say we can assign a data points to the nearest cluster in the whole group in the whole picture, and then we compute the central of each cluster by taking the average or whatever other ways you can define. So you can see this measure is actually frequency-based because you are checking the number of the objects in the cluster sharing the same attribute value. And it can actually be further extended to have a fuzzy working mode. The fuzzy k-modes method is basically saying that one object do not have to be belongs to one single cluster. It actually can belong to multiple clusters. So this this indicates the fuzzy in the title of the method, and then you can calculate a fuzzy cluster membership for each object to the other objects. And it also can be extended in a way that you're trying to handle both the numerical value of the data in the data points as well as the categorical value in the data points. So think about, you not only have the function for a product, you also have some specification for the product, like the dimension, the battery life, and so on. It's very nature that you see both kind of data appear on the same data objects or the same data points. So they propose this K-prototype method as well, and I'm not going to cover the details of these two more sophisticated methods, but if you are interested, you definitely can go back to the textbook and look at the resource on the Piazza. And as you so another angle that we can further improve the k-means algorithm, other than handling the categorical value, other than handling the outliers, is that think about the shape of the cluster you are going to handle. Can you handle different kind of shapes? For example, in this picture here, you can see it's very natural you put the circle, the outer circle as one cluster versus the inner kind of dense circle as the other cluster. And you will find out that k-means actually cannot give you the desirable results in this case, because by the nature of the k-means objective function and distance measure, it can only handle the linear separable case very well, where you have maybe the left part is one cluster, the right part is the other cluster. But if you look at this specific case, k-means, let me skip maybe one, maybe this figure will be more intuitive. They actually run experiments, let's say. Originally, you have these data points shown in the first picture, and they run k-means on these data points. And the second picture is what you get from k-means output. They still use a linear kind of hyperplane to separate the whole picture, and you have the left part as the right part is the other cluster. Versus if you have other more advanced way to handling this high-dimensional data, you can get a better result shown in the third picture. Let's go back to this slide. And that motivates people to using kernel trick or kernel method to handle the data distribution where those data distribution should have a non-convex cluster structures. So the idea here is that you, instead of using the original data representation, instead of using the original numerical value or the categorical vector for each data point, you're trying to map them to a kernel space. So the kernel space basically means that another different space where in that space you can think about using even hyperplane, you can separate the data points in the way you like. So it's very hard to explain what that hyperplane looks like, but that's the magic of the kernel method. So the basic process is that they map these data points from the original input space into some high-dimensional feature space using a kernel function as a transformation, and then they can use the original exactly the same k-means algorithm over those transformed data representation, and it would turn out that on the transformed space, k-means works pretty well. But there are also some extra burden when you resort to this kernel method. One is, of course, you have extra space cost because you need to store the kernel transformation results, which is basically an n by n kernel matrix telling you that how did these any two data points in the data sets are similar to each other in the kernel space. And besides this space cost, you actually have the extra computational cost because you have this kernel transformation, which I will introduce shortly. So we talk a lot about the kernel transformation. So what is the kernel transformation and what is the possible transformation we can do One of them is definitely the polynomial kernel of degree h. You can think about the kernel dissimilarity between data points xi and xj can be basically defined as the inner product of xi, xj plus 1 to the power of h. So this is basically the polynomial definition here. And another way of defining this is basically coming from the Gaussian distribution. You can define the kernel similarity of two data points in terms of the Gaussian radial basis. They are shown in this formula. Another way is you can do a sigmoid kernel by computing the tangent of the inner products of the xi, xj minus the theta. I'm not going to talk too much details into these kernel methods, but I want to give you some general idea of why the kernel trick is feasible in doing clustering. Here you can see the kernel methods basically, the core of the kernel methods basically require that the kernel similarity of two data points can be factorized in a way that is shown here. It can factorize into a phi xi dot product phi xj, where the phi function here is what I just mentioned, the kernel transformation function. So far we have no idea about what is this kernel transformation function. And the magic of the kernel method is that you don't actually need to explicitly compute this kernel mapping function. Because if you look at the objective of the clustering here, if we simply just use the sum of the square error criterion in the k-means, you can see you are computing the distance from the phi xi to the central, where the central is computed also in the way that it's taking the mean of the phi xk within each cluster. So I'm going to ask a question here, why we don't actually need to explicitly know the definition of the feature transformation, the kernel transformation function phi. Anyone knows? Okay. Yeah, good. I think you are talking about why the kernel trick, the kernel mapping actually can yield better results in different data distributions. So my question is more on, let's look at this SSE criterion here. I just mentioned that the kernel trick, the magic of the kernel trick is you actually don't need to explicitly compute or define what is the phi function. You only need to keep the value of the k xi xj, which is the kernel similarity value there. And then you can do the clustering without any trouble. So that means you just need to pre-compute the k matrix for all the k xi xj, and then you are done. And then you can just resort to the k itself for the rest. And I'm asking why this can work. So think about, can we further rewrite the SSE criterion the other way, and then re-represent them to the kernel similarity values? Anyone have some thoughts? Yeah. So I think the bad thing is I don't have concrete slides to show this. This just come up from my mind, and the slides is written by Dr. Han, so I can't help much. But so what I want to talk about is you think of we have the L2 norm here with a square, right? So if we rewrite these terms, basically you write it out. You have those phi functions. They basically you have the inner products of phi xi to phi xi. And you also have the inner product between phi xi to ck, where if you look at the ck, it's basically defined in the way that it's also also a summation of different phi functions. So at the end of the day, you have a bunch of terms where every term either it's a constant term, either is the multiplication between two phi functions. And that multiplications between two phi functions is already been divided by the kernel similarity matrix you pre-compute. And that's the reason why you don't actually need to care about what exactly is the phi function here. You only need to care about how you define this kernel similarity using the typical kernel functions I showed above. And that's the magic of the kernel function. I believe there will be other classes like in statistical learning classes or machine learning classes that will talk more in depth about this kernel matches. So before deep learning come out, actually support vector machine with kernel methods has been a huge success, and it takes over the machine learning community for a very long time. And the magic is basically because using kernel function, you can handle various data distribution. No matter it's convex, it's linear separable, it's linear non-separable. If you have the correct kernel function, you do this kernel trick, and you can get a pretty good result. And that's actually the magic of the kernel function. So that's just my 2 cents on this. So this slide basically give you a more concrete walkthrough on how we compute the kernel similarity values. As you can see, if you pick the Gaussian radius basic function, the RBF kernel here, then suppose we are trying to cluster 5 data points, and each of these data points are in a 3-dimensional space. You have x1 to x5 in a different axis in the 2-dimensional space, and in the original space, you can see by the L1 or L2 distance functions, you can compute their distance. Versus if you go to the kernel space using the Gaussian radius basic function, you can see the values is computed in a totally different way. It's e to the power of -1 to -4 and so on, and it actually leads to these results as I previously showed you. You can nicely partition the data points, even those data points has a non-convex cluster structure. Okay, so all I just talked about is the partitioning methods. As I emphasized in the beginning of the class, partitioning methods, they have a specific number of the clusters in mind, and then they design these algorithms trying to partition or group the data points in the data sets into these k different groups. So in many other applications, you are doing a more like an exploration of the data. So you want to see if I set k equals to 5, set k equals to 10, or even 100 or even thousands, how these algorithms will partition my data sets. So that is very natural That's very natural thought extending from partition-based method to the hierarchical method. You basically want to progressively check the data set using from very relaxed criterion to very strict criterion to manipulate those data points and see how the resulting structure goes. So for the hierarchical clustering methods, I will talk about the basic concepts, basically what is the hierarchical algorithms, what is the basic idea and the procedures behind these algorithms. And I will talk about 2 specific paradigms of this hierarchical clustering. One is kind of bottom-up, which called algorithmic clustering, or they can do a kind of top-down paradigm called a divisive clustering algorithm. and some other extensions to this hierarchical clustering framework. Like, can you do a better job in the scalability? Can you do a better job in the space or the time consumptions? So that gives you to several different concrete algorithms proposed in the literature, including the Birch, the Cure, the Cameron, and some probabilistic hierarchical algorithms. So first of all, I believe from the name of the algorithm, you can think you have a very clear picture about what is hierarchical clustering. You can also think it as a kind of a dendrogram, where let's look at the picture on the right side. Let's say you either can start from A, B, C, D, E, these 5 different data points, and trying to iteratively group them together by some similarity measure. Let's say you can put A, B together first, and then you can put D, E together in the second step, and then you find out that C should also belong to the cluster where D, E is in. So you merge C into D, E, and you create a cluster C, D, E, and then eventually you're gonna merge everything together and form a huge single group where all the data points are in this group. So that's the basic idea of doing a bottom-up paradigm. Versus if you're starting from the whole data sets A, B, C, D, E as the step 0, and then you look at, say, should I partition this big group in some way by some criterion? And then you have A, B as one group and C, D, E as the other group. And then you look at C, D, E, say, whether I should further partition them into 2 groups like C and D, and then you go back to the A, B, C, D. So that's more like a divisive and a top-down paradigm. So in the procedure, you can see I totally don't need to specify the number of the cluster, the K. And actually, it gives you the flexibility to actually stop at any of these steps. And the stopping criterion actually gives you the granularity of the cluster. Let's say if you step in the, if you stop in the step 2, in the bottom-up process, then you will have cluster A, B, and D, E, and C, these 3 different clusters. If you stop at step 1, you will have A, B, C, D, E, totally 4 different clusters. So you don't need to specify the K, but you need to specify a certain stopping criterion where you're going to stop this merging or partitioning process. So, and this is one difference from the partitioning-based method. The other difference is that this whole process is more deterministic than those partitional-based methods. Recall that in the K-means algorithm, it's pretty sensitive to the initialization. If you pick in the two different tests, if you pick 2 very different initial points as the central of the cluster, and then run this K-means algorithms, it could probably give you very different final results in these 2 tests. Versus here, no matter how many tests you have been done, if you already specify the distance functions that you use to partition the data points, and you specify the stopping criterion, then you're going to stop the partition, then you will have the same results every time you run the algorithm. So as I said, roughly we can categorize this hierarchical clustering into 2 categories. One is doing this bottom-up process. One is doing this top-down process. So a more intuitive way to look at this process is to think about that the whole things will finally give you a dendrogram, where either you decompose data points from the root of the dendrogram into the singletons of data points, or you're starting from the bottom, you're trying to grow this tree to the root. So that's a more intuitive way to understand the process. And let's look at some concrete example, concrete algorithms of the agglomerative clustering algorithm. There's one called AGENIS, proposed in 1990. They use this so-called single link method to define the dissimilarity matrix. So I would talk about what is single link in shortly. And then let's say they have some way to define this dissimilarity matrix. And then they continuously merge the nodes that have the least dissimilarity, or just merge the nodes with the best similarity. And eventually, all these nodes will coming up together to form one single gigantic cluster. So as you can see, in this hierarchical clustering process, the key difference from the k-means algorithm is you need to define the distance measure for two subpopulations. So remind that in the k-means algorithm, all the operations, all the similarity measures is between two data points. But now, in the hierarchical algorithm process, you need to define the similarity measures between two subclusters. One may be AB, the other may be CDE. You need to define how similar is cluster 1 AB to the cluster 2 CDE. So that leads to different definition, and that leads to different concrete clustering algorithm here. So there roughly are four popular ways of defining this similarity. One is called single link, one is called complete link, and then you have average link and central link. So yeah, maybe I should ask a question to you guys. Maybe you guys can have a guess on what is this algorithm do by just looking at the name. Can someone have some guess? I think the average and the central link may be easier to guess, but what about single link and complete link? Anyone? Okay. The maximum one. So maximum one means this one. What is maximum? Okay, good. Yeah, since you have done some homework before the class, that's good. So let's look into this definition. First, what is the single link and what is the complete link? These two cases actually are kind of contrast to each other. The single link, if you look at two clusters, the single link basically means what is the similarity between the most similar or the nearest neighbors members within these two clusters. So basically, you want to pick one from the cluster A and one from the cluster B, and then you need to make sure that the distance between this A and B should be close to and then within using this single link definition, you can then try to measure the similarity between any two clusters. So by this definition, it's easier to see that it's looking at very local manner. It's basically say no matter how these clusters are already shaped, maybe they are kind of a rectangle, triangle, circle, or any kind of shape. This single link definition actually don't care too much about their shape. They just look at the most similar neighbors between these two clusters, and then if they are smaller enough, they're trying to merge these two clusters together. So they emphasize more on the closed regions while ignoring the overall structure of these two clusters. Because of these reasons, it actually has some limitations. It's very good at just clustering those non-elliptical shaped group of objects, but not good at doing something else. So, and of course, it's also very sensitive to the noise and outlier. Think about there's one outlier in the group B, which is so close to the other cluster, versus the remaining of other members in cluster B is totally in a long distance away. They form a dense cluster, and this will, and the single link algorithm will still think we should merge these two clusters, and that's That's the harm caused by the outlier in this case. And in contrast, complete link definition here is looking at the most distant members between these two clusters. So these figures actually give you a very intuitive explanation by what is the most distant members. So it basically this complete link algorithm trying to merge the clusters so that the resulting or at the end the merged cluster will have the smallest diameter, because the complete link is basically asking about whether I can find a cluster to merge that the resulting structure has the smallest diameter. And you can see, compared to a single link case, the complete link actually is behaving in a kind of not very local manner, because it's looking at the longest distance between two clusters. So it actually consider the shape of these two clusters when they're doing this when they're checking whether should merge these two things. So the resulting cluster will be a more compact shape compared to the single link. But the problem is still very sensitive to the outliers, because you think about if in cluster B there's one outlier which is very, very far away versus the other are just very like in a normal way, then if this complete link algorithm trying to merge this A and B together, it will cause a shape that you have one single object in a very far away, but most of the data points is packed in a very small region of the cluster. So other than this single link and complete link algorithms, we also have two other definitions. So the average link is basically defined in the way that you need to compute all pairs of the class members and trying to average the distance on these pairs and use that average as a measure of the closeness of the two clusters and check whether they should be merged. And you can see, because you need to do this pairwise computation, it's very expensive. And in the other way, the central link is you just need to compute the distance between the central of the two clusters. So this can be done in a more efficient way, because you first need to figure out what is the centrals within each of the clusters, and that won't need you to compute all the pairwise possibilities. So this is more efficient way. And other than the way how they define this distance function or the similarity function between two subclusters, you also need to specify how to pick the central of the new cluster. So there's two criterion here. One is called group average ephemerity clustering, the GAA algorithm. They pick the central by computing by computing using the formula shown in the right side. It's basically a weighted average. You need to where the NA is the coordinative of cluster A, which is the number of the objects in cluster CA, and the MB is the number of the cluster in the number of the objects in the cluster B, and you compute this as the new central, and then you check whether using this new central you can actually improve or actually hurt the objective function. Another criterion is called the Words criterion. It's using a slightly different way, because this formula is basically derived from checking the differences of the SSE criteria when they try to merge CA with CB to a new cluster. So basically, it's using WC, A, and B to minus this WC, and then they get this formula. So other than this algorithmic clustering, you have this divisive clustering, which is from the from the whole data set as a root. You're trying to partition them in in a progressive way to finally get to every data point is a singleton, or every data point itself for a cluster. So it's implemented in a very similar way. You study from the whole data sets. You're trying to ask how to partition this huge cluster that can best optimize the objective function or the arrows. And that means you need to define this objective function or arrow function before you run this algorithm. But the way you define this objective function could be very similar to what you see in the k-means or what you see in the algorithmic clustering. So let's assume you have such a way you can partition them, and then you can when you have these subgroups, you can further iteratively to further partition those subgroups until you meet some stopping criterion, or you already reach to the bottom, which means every data point itself is a cluster. So, of course, as I just said, that there's many ways to do this divisive clustering. You can choose, when you choose which cluster to split, you can check the sum of the square arrow of each of the cluster and pick the cluster with the largest the sum of square arrow, meaning that its data points is not very compact, it's not very cohesive, so you need to look at that cluster and split them first. That's one thing. And there's also another aspect is how to split. So how do you, should you put these 3 points in a cluster or put this 4 point in a cluster? That, in that case, you can use different criteria. For example, the words criterion is one way you can define, and the SSE criterion is another way you can define. And for categorical data, because you cannot compute numerical value for the SSE and words, you can use the Gini index instead. So there's also other aspect of extending or refining the divisive clustering paradigm is to think about how to handle the noise in the data sets. For example, deciding a threshold to determine the algorithm is one critical thing to stop, to eliminate the noise. So that's basically the overview of the hierarchical clustering. You have those agglomerative scheme paradigm and the divisive paradigm. You have different ways to define the similarity between 2 subgroups or subpopulations, and you have different ways to choosing which cluster to split first and how you split each cluster using different criterions. So one major weakness of all these hierarchical methods is that it's not very scalable. So almost all of these algorithms, as you can see, they have the time complexity of at least O(n) squared, and the n is number of the data points. So it's easily can cross the boundary when you are dealing with a huge product database or a huge customer database, where the n can be scaled to billions or even hundreds of billions. So along these lines, along the line that people trying to make the hierarchical clustering more effective and more like practical to use, is trying to make it more scalable using different tricks. The tricks could be coming from how you leverage the data structure to better organize the process, like using the CF tree to do some incremental update, or you can doing some subsampling of the data to make the whole process looking at less data points in the intermediate step. And they can also leverage this graph partitioning methods to do a better job. So I think I'm gonna stop at here today because I don't want to cover too many details in the following up slides, because it will talk very detailed in these several algorithms. So before ending the class, I want to say any other questions that I can answer regarding today's content. Yeah. So yeah, feel free to talk to me in person. Thank you.